আচ্ছা আগে আমি বুঝিয়ে নেবো এই জিনিসটা, তারপরে তোমরা লিখবে, ঠিক আছে? সো আমরা আজকে পড়বো হচ্ছিল ফোর্স অন এ কারেন্ট ক্যারিং কন্ডাক্টর ইন এ ম্যাগনেটিক ফিল্ড, ঠিক আছে? সো হোয়াট ডাজ দিস রিয়েলি মিন? মানে দেয়ার উইল বি এ ম্যাগনেটিক ফিল্ড, হ্যাঁ, অ্যান্ড দেয়ার উইল বি এ মুভিং চার্জ। কারেন্ট ক্যারিং কন্ডাক্টর মিন্স মুভিং চার্জ, ঠিক আছে? দেয়ার উইল বি এ ম্যাগনেটিক ফিল্ড অ্যান্ড দেয়ার উইল বি এ মুভিং চার্জ। Current carrying conductor means this is a current carrying conductor. That means some charges are flowing like this, right? Negative charge or positive charge are flowing like this in this direction. So when I am mentioning current carrying conductor, that essentially means moving charge, moving charge, okay? So when any moving charge passes through a magnetic field, that moving charge experiences a force. So let us take this example. Here there is a charge which is moving in this direction, okay, and there is a magnetic field which is, the direction is shown, magnetic field north pole. Suppose this is north pole, this is south pole, so magnetic field direction will be north pole to south pole, simple. So if this moving charge is in a direction, that is the direction of the movement of the charge is not parallel to the magnetic field, that means this charge cannot move parallel to the magnetic field for my experiment, ठीक है? If this moving charge is not parallel to the magnetic field, then this charge experiences a force which is mentioned as, which is named as Lorenz force by the name of a scientist, ठीक है? So a charge moving in a magnetic field, but that direction of movement is not parallel to magnetic field direction, then only it will experience a force which we will call, which is named as Lorenz force at this moment, okay, which is named as Lorenz force. So here is the experimental setup. So here is one stand, with that one conductor is basically, ठीक है? So one conductor is basically hung with this stand, and here is a electrical circuit where current is flowing. So we can clearly understand that there is a direction of current which is flowing from positive to the negative terminal of the battery. Clear? Clear to? Next, now at this moment I have taken an horseshoe magnet, and I have placed the horseshoe magnet. So if কোনো কিছু আছে পেন টেন টাইপের কিছু, পেন 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 2-3 পেন দাও, 2-3টে পেন দাও, 3টে পেন দাও, হয়ে গেছে, আর লাগবে না, হয়ে গেছে। আর দৌড়টা লেখা সবাই লিখে দিয়েছি, হচ্ছে চিন্তা। তো এটা একটা হর্সশু ম্যাগনেট, হ্যাঁ? সো দিস ইজ দ্য ওয়্যার, অ্যান্ড আই হ্যাভ প্লেস দ্য হর্সশু ম্যাগনেট লাইক দিস, ওকে, লাইক দিস, okay? So if the north pole is in the bottom and south pole is in the top, clear? So like this I have placed basically, okay? So like this. Now kar konta niye na. So north pole at the bottom, south pole at the top. So magnetic field direction, correct? Huh? So if current is flowing in this direction, magnetic field direction is at the top, then the force will be in direction towards you, ठीक है? Easy way to get into it by drawing 3-dimensional coordinate diagram basically. So this is x axis known to all of you, this is y axis known to all of you. At this moment we are adding another axis which is basically towards you and away from you, okay? So this conductor, the shaded portion, is going to experience a force towards you when the magnet is brought. If the magnet is not there, no force. If the current is not there, no force. So no current or magnet, no current or magnet, you will get no force, because there are three important parameters. There has to be moving current, that is moving charge, there has to be a magnetic field, and the current and magnetic field cannot be parallel to each other. These are the three very important conditions. In this diagram, if you see, force is out of the plane of paper. So for you it will be plane of paper, for me it will be plane of board. The force is out of the plane of paper. So if you see this diagram also, it will be very much clear. Current is in this direction, magnetic field is in this direction, and you can see the force is coming out of the paper. Okay? Now if B becomes parallel to current, that is current direction and magnetic field direction is same, then there will be no force. We have already discussed. Done. Okay, done. Next is, suppose I reverse the direction of current. Suppose I reverse the direction of current, only current. Suppose I reverse direction of only current, then force will go below the plane of paper. Okay. Now suppose I reverse the direction of only magnetic field. How? Here the south pole was at the top, north pole was at the bottom. I just make a 180-degree turn. My north pole goes to the top, south pole comes down. So direction is changing. Current I have not changed this time, only I have changed the direction of magnetic field. In that case again the force will go below the plane of paper. But if I change magnetic field and current simultaneously, then one cancels out other. So again the force will be out of the plane of paper. Done. Now if we see all these things, if we conglomerate all these things, we will get force will be directly proportional to the current applied. So more and more current will be passing, more and more force will be generated. Okay. It is directly proportional to the strength of the magnet. Strength of the magnet will give you strength of magnetic field. So that is basically denoted by B, strength of magnetic field. Done. Next is length of the conductor. Force will be directly proportional to the length of the conductor. It is found out. Okay. As you make the length of the conductor more and more, the force will be more. Okay. Next is, so if I conglomerate all these things, I can get this one, F is equal to K IBL. Now in SI unit, K is equal to 1. So I can write F is equal to IBL. Clear? Okay. So now to find out units, which is very important over here, B is equal to F by IL. So Newton by ampere meter. Together it is called Tesla. Based on this, now a company is running, and that is not owned by Tesla. Next is this Tesla is also written in another form of unit, which is also very important because this is also named on a scientist name. So many people already contributed into this electromagnetism. This is Weber per meter square. Now I have tried to derive the unit of Weber in a much easier sort of unit that we are familiar with. So if you see this one, Newton by ampere will be there, will have to be there, right? But here there is meter square. That means you are dividing Weber with something so that it gets this. So if you see my expression, Newton meter by ampere, if I divide it by meter square, then I will get this. Newton by ampere will remain as it is, meter by meter square, niche meter. ठीक है? So this is all about the first topic of electromagnetism part 2. Now you can write it down. So till now we have basically considered that there is a Lorenz force and there is certain direction of Lorenz force, but there will be various examples where we have to find out the direction of force. So for that an easy rule has been devised by Fleming, that is named as Fleming's left hand rule. So this is your thumb, left hand, this is your thumb, this is the forefinger and this is the middle finger. Tick. So you have to always place this thumb, forefinger and middle finger mutually perpendicular to each other. That means if you place this one like this, okay, this is 90 degree y axis, this is x axis, and see this is the z axis. Okay. So that is how it is put. Now which one will represent what? So I have, this is our own devised rule which makes it easier. That is, rename this rule as FBI rule. Because I am very well conversed that my thumb will come first, forefinger will come next and the middle finger will come third, right. So my first one will be force, second one will be magnetic field, third one will be current. So that makes it FBI rule. Okay? So thumb will represent force, forefinger will represent B, magnetic field, and the middle finger will represent the current direction. So this all represents the direction of different parameters. So based on this, I have taken 4 examples which will make it very much clear whether you can apply this rule and find out the force or you can't. Okay? So if you can't, you have to keep on trying. If you can't, you have to keep on trying, because there is no way out. So it will be easy, not tough. So this is my finger, so you have to do all these things along with me. You have to repeat. So this is the case. So what is my direction of magnetic field? My direction of magnetic field must be like this, right? This is my direction of magnetic field. So my magnetic field is my forefinger, the second one. So somehow or the other I have to put this down like this. So first you just put down, then it will not be much hard. You can easily do that. Next is, what is my direction of current? My direction of current is at this moment is basically Z axis, right? So this was my first guess. So at this moment my current is not in X axis. My current is in this axis, right? It is going inside, direction going inside. And where is my magnetic field? The middle one. Current is this one. So current will go like this. Current will go like this, correct? This is current. The middle finger will go like this, inside. Now what happens to my this magnetic field? Magnetic field is which direction? So I have to change my finger. This will remain as it is. This one, correct? So what is the direction of my this force? In the negative X axis, right? Negative X axis. So direction of force is in this direction. Okay? Clear? Now you have to apply the same thing to find out whether you have learnt it or not in this one. Okay? So let's try again. My direction of magnetic field has not changed. It is as it is, correct? Magnetic field is in this finger, right? Forefinger. ঠিক আছে? So this is this side. At any case, this will be this side. Where is my current? My current is going outside. Means middle finger. Correct? Where is my thumb pointing? Positive X axis. Force. As I have changed the direction of current, my force direction has changed. As I have changed the direction of current, my direction of force has changed. Go for the next one. I not only have changed the direction of current this time from this one, I also have changed the magnetic field. So magnetic field direction is bottom to top, right? So magnetic field means the middle finger again. The middle one means my middle one, not this one. Okay. So this one, the forefinger. The forefinger goes like this, and my current is not going on to this side. My current is going to this side. Correct? And the force? Negative. Now compare with that one. Current direction has changed. Magnetic field direction has changed. Both has cancelled each other. My force direction remains the same. Okay? The last one. Let's try this one. Here the figure has to be understood very well. See, at this moment of time, all this current were passing through Z axis. At this moment over here, the current is passing through Y axis. That means the middle finger will lie like this. Don't take it otherwise. Okay? So middle finger will lie like this. And if you see this magnet, if this magnet is kept like this, then there will be no force, right? Because the magnetic field will be parallel to the current, no force. But it is not like that. That is why you cannot basically see this one. You cannot see the place where wire is passing it. I have given some break over here. That means this is behind the wire and this part is in this place, in front of the wire. So magnet is like this. Magnet is like this, and the current is passing like this. Magnet is like this, current is passing like this. So Where is my current? My current is in the my middle finger. So and my magnetic field is in my forefinger. Okay, so my forefinger at this moment has to go like this, correct? Has to go like this, correct na? এদিকে যাচ্ছে forefinger, because north pole to south pole magnetic field in through this board, and this is my current. This is my current. Force negative x axis, right?